Right. All of chapter 5 was about probabilities. And the probabilities we did were based on discrete things, right? The number of marbles in a jar, the number of flags, the ways 10 horses could come in first and second in a race. Those are all discrete kinds of probabilities. Well, chapter 7 brings in this normal distribution, because the kinds of probabilities we're going to be looking at really for the rest of the semester are not necessarily discrete. They're continuous. And that poses some problems for us. Because for continuous probabilities, we need to find areas. And under this normal distribution that we're talking about, the only way to actually find the areas is with calculus. Well, we don't do calculus in this class, so we have to rely on something else. So let's start with what this idea of a probability density function is. And in that sheet I just gave you, the outline, it says it's got two characteristics. First is, if you see a graph of it, the area under that graph is 1. Okay, that's going to make things easy. And it also says, when you look at the graph, all of it's above, all of it's either touching or above the x-axis. There's no negative dips into it. Okay, and the random variables talk about it's whatever we're measuring. So let's take a look at one. This is a drawing of a uniform probability function. Uniform is that everything in there has an equal chance of happening. If I was throwing darts at that thing and I knew that the dart was going to hit somewhere in there, every point in there would have an equal chance of hitting. That's all that's saying. Notice, what's the area of my rectangle? Two times 0.5 is 1. So this meets the definition of what a probability density function is. And so let's say I've got a probability of some event E happening of 0.25. Now we're thinking area. You got to convert in your head from marbles in a jar to area now in chapter 7. How far would I have to come on the x-axis there to a value so that I'm going to get an area of 0.25? Well, I have to come out to 0.5, right? Okay, and then I'd shade in this part right here. So that shaded part is 25% of the area, but that also represents the probability. So we're equating area proportions with probability now. And that's where having an area of 1 comes in handy. All right, there's that one. Let's look at another one. Let's say I've got some event M and its probability is 0.6. How far would I have to come out there on the x-axis to have an area of 0.6? So you got to think about it. You're saying, all right, 0.5, the height, times something will give me 0.6. And I'm getting 1.2. So I'll draw a line out here at 1.2. Shade it in. That area represents a probability of 0.6. Why? Because it takes up 60% of the area. If I were throwing darts at that thing and they had to hit inside that rectangle, the probability of them hitting in the blue part is 0.6. That's all it's saying. Because it has more area. Multiply 0.5 times 1.2. I kind of worked it backwards. So again, we're just talking about area. But then we get to this kind of thing. Those first two examples were uniform distributions that we can just do area of a rectangle. This is a graph of a normal distribution where most of the things are grouped in the center. To find proportions of areas in this, we'd need to know calculus. If you take higher levels of statistics, you'd have to use calculus to find the areas. We're not going to have to do that. So we're going to base ours on a z-score, which is going to place us somewhere on that curve. And if we want the area to the left of the z-score, then I'm talking about that right there. That's the same kind of idea. If I'm throwing darts at that randomly, and I know it's going to hit somewhere under that curve, that z-score is going to represent a way to find the proportion of the area. And we've done z-scores before, so that's not totally new. All right, look at these distributions. Now, y'all, this is all the same distribution. Looks like it's going from from 50 to 150. These all three represent the same distribution. The difference is how wide the bars are. If you look at A, the bars are pretty wide. They've got a normal distribution behind it there. I don't know if y'all can see it from where y'all are. It's in the book. It looks better in the book. But those bars don't really approximate that normal curve so much. We go to B, and what did they do there? They shrank the bars. They're more narrow. The normal curve is a better representation of that. And then we go to C, and that's looking more and more like a normal curve. Now, what if I kept shrinking the bars to where they're more accurate? We would eventually get to a place where that normal curve is a really good representation of it. And so we'd end up with this. And when you're looking at that curve, remember, that's a concept. The reality in life is those histograms up there, when we're actually counting things. That normal curve is a model. Just like y equals mx plus b is a model of what? Two variables that their relationship is described by a straight line. That's all that is. So we have math models all over the place. All right, let's keep going. Look at these two. The first pair, what's the difference? I mean, they look exactly the same except for one thing. Peyton's saying the mean. Yeah, the mean of the one on the right is 3. The mean of the one on the left is 0. Otherwise, they're identical. Do both of them have an area of 1? Yeah. Look at the second pair. They both have an area of 1. But here, the standard deviation is different. The bottom one there has a standard deviation of 2. And when I shrink that standard deviation, look what's happening to the curve. It's having to go up because it still has an area of 1. So as the standard deviation gets smaller, things get packed more closely around the mean is what's happening. Questions so far? So the answer to that question is, in the first pair, the mean changes. In the second pair, the standard deviation. And all these things that are normally distributed, like heights and weights and IQ scores and SAT scores, those are all going to have a different looking distribution, but it's going to be similar to these curves right here. For SATs, if you get an SAT math score of 500, that means you're right in the middle. If you get a score of 700, you're way out to the right-hand side of that curve. And then we've seen this thing before. This is the empirical rule. Look at the shape of the curve. It's a normal distribution. This is where we've got 68% within one standard deviation on either side of the mean, 95% within two standard deviations, and so on. We've worked problems with this. This is not new stuff. And then if you look down there at the bottom, it's got the percentiles. If you can add them up, it's got the percent of the area under each one of those sections. So we can figure out the percentiles from that. Okay, that's old news. 7.2 is saying, all right, you've looked at a normal distribution. Let's look at this thing called a standard normal distribution. What makes it special? Two things. It's got a mean of 0 and a standard deviation of 1. That's going to make working with the numbers real easy. But I know heights and weights and SAT scores and the heights of plants that grow and things, they don't have a mean of 0 and a standard deviation of 1. Women's heights, I think, have a mean of 65, I think, inches, and a standard deviation of about 2.5 inches. That's not 0 and 1. So a z-score says, all right, if you put your values into this z-score, I can convert your mean and standard deviation into the standard normal one. You go, okay, ho-hum, what does that do? Well, if I had distribution here where the mean is 65 and the standard deviation is 2.5, and I want to know out here where I am, I'm going to have to use calculus to get this area right here. We just said, I don't want to use calculus in this class. So what did somebody do? They took this standard normal distribution and they said, let's use calculus and figure out what all these different proportions of area would be. There's actually a formula to do that. And they made this table for us. This table in your formula pages is the result of them plugging values into that formula, which is based on calculus, and getting areas for us. Well, that's nice. And that's what z-scores let us do. They let us convert any normal distribution to this standard normal distribution, which means I can use that table. This is in the textbook. Don't expect you to read it out at, in the back. But look what it's telling us. We're talking about area here. If we have a z-score, and I want to find the area to the left of that z-score, I can just look it up in the table. This table right here is what we're talking about. I can just find the area that corresponds to a certain z-score. If I want to find the area to the right of that z-score, then I have to subtract from 1. That's what the middle parts tell us. And if I want to find area in between two z-scores, I'm going to find the area of the bigger one. I'm going to find the area of the smaller one, and I'm going to subtract those two. That'll give me the area in between. So you might want to look at that where you can actually see it in the book, but that's what it's saying. Here's the table that we're talking about that everybody loves. And what I did was, just to make sure that we all see what we're doing here, is to say, okay, suppose I pick a value. Let's say I have a z-score of 1.25. So come over here to the 1.2 z-scores. And then I come over to the column that has 0.05. And I find out that number right there, 0.8944. What does that represent? First of all, what does a z-score of 1.25 mean? Good. 1.25 standard deviations to the right of the mean. And when we're talking about the mean, it's dead center. Well, where's the median in a normal distribution? Same place. How about the mode? Same place. So all those ways of measuring the center of distributions coincide in this mathematical model. So the mean and median are pretty close together. Theoretically, they're identical, but that's theoretically. Okay, so that 0.8944 represents two things now. It represents the amount of area to the left of that z-score, and it could also represent a probability. So the more you can start thinking of probabilities in these terms, the better. So that's what this is saying right here. And again, this only works if we're talking about a normal curve. Okay. Let's work a couple of problems similar to what you're going to do in the homework. This is at the end of this section. We've got a mean of 50. Again, this is normally distributed. And we're talking about some variable x that has an average of 50 and a standard deviation of 7. So I'm just going to take this little curve and sketch those in. At least 2 standard deviations worth. And let's work a couple of these problems. So everybody's got a calculator, everybody's got your formula pages, or you're sitting by somebody that does. Let's work a couple of these. So the first one says, find the probability that x is bigger than 35. Bless you. So 35 is going to be right in here, right? So greater than 35, I'm looking for the area to the right of that. So first thing I do is get a z-score. So z of 35 equals 35 minus the mean divided by the standard deviation. What are y'all getting? Negative 2.14, about. That's the z-score. That means whatever this is measuring is 2.14 standard deviations to the left of the mean. All right, so I've get my table out, and I'm looking for negative 2.14. And I'm getting 0.0162. So that means the area equals about that. So we're talking about that from that point up. What did I do wrong? I want the area to the right of that, so I've got to subtract that number from 1. So I need to do this. 1 minus that is going to give me 0.9838. In other words, the area represented by that red line there, if I colored all of that in, is 98% of the area under the curve. If you stop and think about it, 35 is more than 2 standard deviations to the left of the mean. What's the probability of somebody scoring, or what if this is a score, scoring that much or higher? Well, about 98%. Because that's how much the area is.
Do you want us to
Same thing. Same thing. It's a good question. I mean, this number right here, this one, that one. Don't all three of those mean the same thing? Just different ways of writing them. All right, let's work another one. 24, greater than 65%. I'm 65. So now, I'm going to erase this. And now I'm wanting 65 is going to be right over here. Right? I'm wanting greater than that, so I'm wanting this area out here. So what's the z-score for 65? And it turns out to be about positive 2.14. So look at positive 2.14, and what area is that giving you? It is. And since we're wanting that area, I've got to subtract it from 1. Every single time that you want the area to the right of that z-score. And both those first two did that. So what am I going to get? 0.0162. In other words, if I were throwing a dart at that graph and it had to hit in that graph, the probability that I'd hit out there where the red is only about 1.5%. If you want to go to the left, you just look it up in the table. That's how we got the 98. In other words, if I took that z-score and I said, how much area is to the left of that, it would be 0.9838. You add those together and you get 1. Exactly. Always. Because why? The area under the curve is 1. Yep. Okay, let's try one where we say less than or equal to 58. So I'll look up the z-score for 58. So I first get it here. Equals about, I'm getting a z-score of about 1.14. That's for 58. So notice what this is saying, less than or equal to 58. So we're talking about now something from here back. So since I'm going to the left of that, I can just look it up in the table. So I'll find 1.14. And I'm getting 0.8729. So the area is, I just look that up directly in the table because I'm going to the left. We good? This is not much different from what we did before, really. It's just in a different context. So I'm going to erase that. Let's work this last one here.
Wait, is there not anything different about it saying
That's a good question. If it's equal to, can I find equal to? No. Because remember, we're talking about area, and equal to would be one little line coming down there. What's the area of a line? Doesn't have any width, so I can't get the area of equal to. So if they wanted the probability of exactly 58, you're going to have to say, I don't know.
So if you're going to the right, you do 1 minus the number you get, and if you're going to the left, then you just like the number you get.
Right. Correct.
And if you have the equal sign,
It's not going to affect it at all in this. Yeah, it's kind of weird. Okay, let's look at this number 27. It's saying between 40 and 65. And if there were equal signs there, less than or equal to on those, it wouldn't change it at all. So really now what I'm wanting is find 40. So 40 would be right in here. 65 is right in here. So I'm wanting this area in between. So what do? You find the big one's z-score. So z of 65, we just found 1.14. What's the area for that? The area was this, wasn't it? Isn't that what we just found? Okay, so what I'm doing is I'm saying I'm getting the area from here back. That's what that 0.9838 represents. And then I'm going to find the z-score of 40. And so what I have to do, I've got to actually plug that in and find it. And what do I get? I'm with you. Negative 1.43. Then I'll look that area up in the table. .0764. Now then what did I just find? I found from 40, I'm finding from here back. Yeah? So that means I've got to subtract from where the black is from the total that we just found for the red. So in other words, what I'm doing by doing that is saying, well, then I just want this part of the red. So that means I just subtract. That's what I'm getting. So between those two values, almost 91% of the area lies. For this random variable, that means the probability of its value being between 40 and 65 is 0.9074. Again, area and probability in this context are the same thing. Let's look at a different kind. So there's going to be a bunch of problems like that. There's going to be some like this, where we're talking about finding a value that puts you at a certain percentile. So I'll put my values up here. and I'm also going to put the percentiles down here. Now, these are rounded off. So when you're 2 standard deviations to the left, that's about 2.28%. When you get to 1 standard deviation to the left, that's about 16. Actually, it's 15 something, but it's close to 16. Well, middle is 50%. 1 standard deviation to the right is 84, about, and we get out here, 2 standard deviations is about 97.7%. So I just put the percentiles in there just to help you all see what's going on, to give you some context here. So the first one is the 9th percentile. Well, the 9th percentile is going to be somewhere in here, isn't it? Between 2.28 and 16. So now we got to work backwards. So you're going to get this table out. And over here in the big part where the areas are, you're going to start there. So find an area in there that's as close to 0.09 as you can find. I'm finding negative 1.34. So see, we're looking it up backwards. We're starting with the area and finding a z-score. So everybody seeing negative 1.34? No? Look in the area part. You want a number as close to 0.09 as you can get. Okay. So what's a z-score? It is, here's our formula. So our z-score here we know, and that's negative 1.34. I don't know x. I know mu is 50. And I know the standard deviation is 7. Now what do I do? I've got 4 variables. I know 3 of them. I can solve for the 4th just with algebra 1. So I multiply both sides by 7. I'm getting negative 1.34 times 7 equals negative 9.38 equals x minus 50. I add 50 to both sides. I'm getting 40.62. What does that mean? It means whatever this random variable x is measuring, if I had a value of 40.62, that would put me at the 9th percentile. Meaning 9% of the population of whatever we're measuring, 9% of the population would be at my value or less. That's what that means. So to color this in, it means from here back this way. So problem 35 is saying, what value of x would put you at the 81st percentile? Let me erase some of this stuff. So now we're looking at the 81st percentile. Well, 84 is actually on a 1 standard deviation out, so the 81st percentile would be right in here someplace. Back. So I look up as close to 0.81 as I can find in the table. And I'm finding for a z-score of 0.88, I'm getting 0.8106. Is there anything closer than that? So if you look down at 0.88, I'm seeing 0.8106, and I think that's as close as we're going to get. So z-score of 0.88 equals whatever value we've got for x minus 50 over 7. So I multiply both sides by 7. And over here I'm getting 616 equals x minus 50. I add 50 to both sides. So when x has a value of 56.16, that would put it at the 81st percentile of this distribution. Meaning what? 81% of the area is from that point back to the left. So if I took that 56.16, if I did this, we're not going to do it, but just think about it. What if I found the z-score of 56.16? Not going to work the problem, I'm just setting it up. What would I get? .88. What did we do? We found the area first and then worked our way back to the z-score. If I took that z-score that we found, or if I took the value that we found and found its z-score, we should get the same z-score that we figured out. Okay, let's look at this kind of problem. And I think there's about 6 or 7 of these in the homework. So really on this, y'all, the first thing to do is make a sketch. So my mean is 125. Standard deviation is 24. So that would make right here 101. Right here 77. I'm just doing 2 standard deviations from the mean. So 1 standard deviation this way is what, 149? And 173. Okay, so there's a quick sketch. Find and interpret the probability that a randomly selected 6th grader would read less than 100 words per minute. So what we're after, I'm going to pull somebody's name out of a hat that's a 6th grader. What's the probability that kid reads less than 100 words per minute? Well, less than 100 is going to be from right in here over that way. So that means I can just look up the z-score and then find the area in the table, and I'm good because I'm going to the left. So what do? Z equals 100, that kid's score, minus 125. We know it's going to give us a negative number because we're to the left of the mean, divided by 24. .04, negative 1.04, sorry. I'm getting 0.1492. Which means what? About 15% of the area is to the left of that score, which means the probability of randomly picking a kid's name that reads less than 100 is about 0.1492, about 15%. Another way of looking at it is, of all the 6th graders that read, about 15% of them read 100 words per minute or less. That's what that means. Look at C. The probability a randomly selected 6th grade student reads more than 140. Okay, so we revise this. More than 140, it's going to be from about in here someplace. This is to the right. So find the z-score. What are we getting? This is kind of interesting. Divided by 24.625. So 0.63, rounded off. So I look in the table, 0.7357. So the area is that. Or is it? No, I made the number one mistake. I want the area to the right of that. So I've got to take this number that I found, and on a test, if you had shown your work and found that number, I'd know that you knew how to do most of it and just forgot the very last. So I subtract that number from 1. Okay, so when I subtract, I'm going to get about 0.2643. Meaning what? If I pull a random kid's name out of a hat, the probability that he or she reads at 140 words per minute or more is about 26%. All right, another kind of problem. Okay, this is between 110 and 130. Let's take a look at it. So what am I going to do? Here's my, this is going to be 149, 173. This is going to be 101. So we're after between 101, between 110, which is going to be right in here, and 130, which is going to be over here someplace. We want this group. So I find the z-score for the 130 equals 130 minus 125. It's going to be a positive number over 24 equals about 0.21 rounded off. Yeah, 5832. Okay, then I find the z-score, thank you. I find the z-score of 110. This is going to be a negative number. I'm getting negative 0.625. So rounded off, negative 0.63. The area of that is that 2643. I subtract them. If I did my math right, I'm getting that. So the area in here is almost 32% of the area. And you go, well, that, horizontally, doesn't look very big. Yeah, but it's in the middle of that thing. So we're talking about close to a third of sixth graders would read between those two values. Would it be unusual for a sixth grader to read more than 200 words per minute? Well, let's see. What would the z-score be? I'm getting 3.13 rounded off. Now look at your table. 3.13. The area to the left of that is 0.9991. That means the area to the right of it, which is really what we're after here, is going to be what? Yeah. Thank you. Meaning, if I reach in the hat, pull out a kid's name, sixth grader, the probability that kid reads 200 words per minute and implied or more is about 1 in 1,000. So, if you kind of expand that, if we had 10,000 kids, we could expect maybe 9 or 10 of them could read that many words per minute. Last problem here. What's it going to take for one of these kids to read at the 75th percentile? Well, I know this is 125, and I know right here is 149. I know this is the 84th percentile, and this is the 50th. So we're talking somewhere in here. I don't know their score. I need to know their score. So we're working backwards. So I'm looking for 0.75 in the table where the areas are. And the closest I'm seeing is at 0.67, I believe. So a z-score of 0.67 would give us an area of 0.7486. That's as close as we're going to get. So I'll put my z-score equals this unknown reading speed minus 125 divided by 24. So I multiply both sides by 24. I'm getting 16.08 over here equals x minus 125. I add 125 to both sides. I'm getting 141.08. In other words, if one of these sixth graders could read at about 141 words per minute, that would place him or her at the 75th percentile. And those are about the only kinds of questions they're going to ask on the homework, which is good because we're about done.